seeing something new, okay? So what this over here means, both ends of the structure is pinned, is known as a boundary condition. And I'll tell you why we're going to fix this into a boundary condition. Okay. Now, if we look at last week, okay, we look at our deformation pattern last week. Okay, our deformation pattern look like this. Okay, our deformation pattern look like this. Okay, so I want you all to focus on our deformation pattern. So this is our deformation pattern. Now, how to make this deformation pattern exactly the same as what we have, okay, in real life. Okay, so we want the deformation pattern to look exactly like this. So the only way that we can do this is by doing this. Okay, so before I go there, what does this mean? Okay, what does all these boundary conditions, or what does, so this end is pinned, this end is also pinned. Okay, and we have an applied force over here coming down as P, right? So for this case, when it's pinned at this end, and this is my transformation. This is X, this is Y, this is moment about Z. Okay. So I'm going to call this point A, and over here at point B. Okay. So let's look at point B first. If we look at point B, right, we know that X is equal to 0, right? Because it cannot move left and right. Y is equal to 0. It cannot move up and down. Okay. And then moment about Z is equal to 0. Okay, at point B. Now I believe that most of you will not have problem with X is equal to 0 because the structure cannot move left and right, right? At point B. Y is also equal to 0 because the structure at point B or at point B, it cannot go what? Up and down. Now, can anyone tell me or type on the chat why moment about Z is equal to 0? Anyone? Or talk to all of us. Why the moment at point B, or the moment in the z-axis at point B is equal to 0? And don't just tell me, okay, there's no moment. How do you know there's no moment? I'll give you all a hint. Okay. Okay. Now, there's no memorizing in this. Okay. You have to be able to visualize this. What happened if we remove the support at point A? Anyone? Isn't B, because B isn't any distant away from the moment, is no. It's because the top is restricted horizontally. Chloe, you are right, but we are looking at B. Okay. Now at point B now, why is moment equal to 0? Exactly, Julia, you got it right. Okay. It's because the pin allowed free what? Rotation. So Julia, quick question for you. If I remove point A, the pin at point A, what will happen to B? What will happen to the whole structure? Or anyone? Okay, if I remove uh the the fixer, B remain the same, but what will happen to the structure? Will the structure still stay vertical? Yeah, Chloe, you're right. You will fall over. So if I were to remove, or if we were to remove, okay, the support at point B, the structure will end up like this. Okay, the structure will end up like this. Okay, it will rotate downwards. Why it will rotate downwards? Why it will not stay vertical? In order for it to stay vertical, M cannot be equal to what? Well, cannot be equal to 0, right? But for the fact that when it's pinned, right? When it's pinned, M is equal to 0. Ladies and gentlemen, you cannot memorize this. You don't memorize things like this, okay? You have to be able to what? Visualize, okay? In this course, it's not just about applying the formula, okay? I will make situation that the formula is absolutely useless to you, okay? You have to be able to what? Visualize. Okay, now my next question to you is this. If you look at point A, right, you know that it's pin, okay? It's so-called pin, right? So over here, we know that X is equal to 0 at point A, right? Y is not equal to what? Y is not equal to what? 0. Yes or no? Because if you look at point A, or the entire system or integrated system at point A, this entire structure, you realize it's on the block and you have rollers, right? You have rollers over here, right? You have rollers over here. Means it can move what? Up and down, right? However, moment is still equal to what? Equal to 0. Okay. So some of you say, Eugene, why moment is equal to 0? Again, if we were to if we were to turn this entire structure upside down, okay, if we were to turn, let me see, can I do this? Okay, I'm going to take this whole thing, I'm going to paste over here, okay, and I'm going to rotate 180, right? I'm going to rotate 180, right? So now, right, if we were to remove the support at B, right, if we were to remove the support at B, right, if we were to take out this support at B, what will happen to the structure again? It will again fall over. Yes or no? So i.e. moment is equal to 0. Okay. Okay. Now, what am I trying to drive over here? Okay. I'm trying to drive over here. So for pin condition, right, we can have condition number 1. We can have X is equal to 0, Y is equal to 0, M is equal to 0, right? The second condition for pin, like what we see, X is equal to 0, Y is not equal to 0, m is equal to 0. We can even have a condition number 3, where we might have a situation where x is not equal to 0, y is equal to 0, m is equal to 0. So can someone tell me, how do you know it's pin or not? And I believe Zachary already have the answer already. Not Zachary. Julia have the answer already. Okay, so when do you define it's a pin? What is the common between condition 1, condition 2, and condition number 3? What is common? Anyone, you can talk to me or you can write on the chat. What is it? Well done. The common condition is moment is equal to what? 0. Okay. So for moment to equal to 0, what we see, the deformation will look like this. Exactly like how we have on the deformation pattern on the left hand side of the image. Okay, so on the left hand side is so-called mathematical vision. So mathematically, you want the deformation to look like this. On the right hand side is the physical, real world. Okay, to get those sort of deformation, you need both ends to be pinned. Okay, so that's where you need to visualize. Okay, in the sense that, okay, mathematically we want the deformation to be on the left, like the figure on the left hand side. Physically, how to do it? Okay, a lot of times, okay, young engineers like yourself have problem visualizing. I was the same. It only grow with age, or how good your instructor is. So I'm really good, I tell you now. My prof did not tell me. My prof would tell me go and figure out, or he himself have not figured it out yet. Okay? Right. So we know that a pin condition moment is equal to what? Is equal to 0. Okay. Now, why this is important? Why this is important? So if we look at the equation which we have formed, right, earlier, we formed an equation where stress critical, note, you have stress critical is equal to n squared pi squared E, then we come up with our L over R squared. Okay. So for condition, where both ends are pinned, right? N is equal to 1. Okay. Why do I say that? Because for this case, right, for this deformation, N is equal to 1. If we look at our different deformation pattern, right, we know that for this case, N is equal to what? 1. We are not doing mode 2, neither are we doing mode 3. We are focusing on what? The analysis that we are working on. We are focusing on mode 1 deformation, where N is equal to 1. So when that's the case, what we realize, therefore, now we have stress critical is equal to pi squared E over bracket L over R squared. Okay. So let me tell you what is L over R first. Note that L over R is most commonly known as the slenderness